So, excuse me, I've discovered that I don't have a review module stashed anywhere, or even review sessions. So, I'll just go over an old exam. Let's see. 3 charges. QT standard test charge. Alright, Q1 is, of course, this is different then. Oh, we get the ruler. Q1 equals negative 6.00 nanocoulombs. Negative 6.00 times 10 to the negative 6 coulomb. Oh, excuse me. Let's get the eraser. Nano is 9. And Q2 equals 3.00 times 10 to the negative 6 coulomb. And let's see, the blue line, which we'll call R2. So R2 is 5.00 times 10 to the minus 2 meters. Okay, and okay, I see where R2 here. We're gonna say that this is let's call this angle 1. 1 equals 36 degrees with respect to negative interesting, it's a typo. I meant to say below. Nobody noticed it, huh? Pretty weird, huh? With respect to, so it's negative 36 with respect to positive x-axis. Most of you probably won't say it that way. I would say 36 degrees south of east. And it's always a good idea to label it. And we see that Q1, excuse me, is located at 3.5 in centimeters. So we'll just go ahead and get ourselves a ruler here. Oops. All right. Oh boy, come on. There we go. We'll declare victory. And let's make it, oh, it's too much, but that's all right. So, E total, so now it won't scroll. Okay, calculate the E vector E vectors, huh? Interesting. Okay, that's fine. So, we have, so if Q1 is negative, the E vector points that way, and this guy points that way. Okay. Draw the two vectors to scale and include angles. Right. So in fact, this guy really has to go. It's just going to get in our way. And better to draw something a little less obtrusive. And we'll just use, oh God, fight and fight and fight. So we got our dotted line and E vectors. As I said, one's going to point like this, and one's going to point like this. So in the first case, and let's see, calculate them. Okay. So E1 is going to equal KQ1 over R squared equals 8.99 times 10 to the 9th. I never remember. Q1 minus 6. Ten to the minus 9 coulombs. And the magnitude there is, let's see, R2x equals 3 times 10 to the minus 2 meters, and R2y equals, well, I can just count them, I don't have to look, 1, 2, 3, 4, 5. 5, well, it should respect the sig figs. Nice and neat. I'm too lazy to erase it. So we need the magnitude of that. So, right. It's 3.00 squared plus 5.00 squared equals square root of 34. 9 and 25. And I suppose I can, the old calculator. Well, first of all, right off the bat, we know that R squared is 34 meters squared. So actually, we can say we don't need the, we might not even need the components, we'll see. So, 8.99, what I mean is we may not need the actual magnitude. And I'm calculating away. 34. Oh, wait a minute. That's 34. It's not meters. Yeah, it is. That's fine. It's meters squared. And then I take the square root. But if I square it, I know it's going to be 34. Okay. But these are in centimeters, so that's yep, I made a goofy here. Let's 34. So that means 34 meters, and it's centimeters. Oh, let's pause this stupid thing. Right, so they were both 10 to the minus 6. So if I square 10 to the minus 6, I'm just multiplying the exponent by 2. So 10 to the minus 12 meters squared. Oh, minus 2, not 10 to the minus 6. So, what's centimeters squared, and then 10 to the minus 2 squared equals 10 to the minus 4, because I multiply them, and times 10 to the minus 4 meters squared. And that's R. So then I just have to directly copy this in, because I'm squaring R's. There's no reason to take the square root of that quantity. Okay, back to L calculator rule. 34 and minus 4. Divide. Wow, that's quite strong. Leads me 1.59 times 10 to the 4th newtons per meter. Now, do I believe it? Let me just check something. That's right. 9 times. I was right about the 10 to the minus 4. And yeah, guess that's right. That's a pretty strong field. Newtons per meter. 10 to the minus, and it's negative. And then the other one, E2 equals K 8.99 times 10 to the 9th times whatever number of coulombs. This one is 3 times 10 to the minus 6. Three times 10 to the minus 6, 3.00, of course. Coulombs. And then we know R2. Well, these are both R1. So I goof it there. And let's fix that. 1, 1. R1. And R2 is 5 centimeters. Okay. So, 5.00 times 10 to the minus 2 meters squared. And this is a 9. And I get 8.99 E9, enter, 3 times 10 to the negative 9, and 5.00 e to the negative 2. That looks fine. And then I square it. And, yeah. Then I divide into it. Okay. And this equals 1.08 times 10 to the 4th newtons per coulomb. Okay. They're both close to each other. And now it's just a question of we have to calculate components. So, oh no, we're not yet. To calculate, we calculated them, and now draw the two vectors to scale. So this one, let's make sure. So that one's 1.59. It's going to be the bigger one for R1. And so and of course it's negative once again, so we can point it up at Q1. So I just decide a length that's going to be, and the E1 has to be 2/3 of it, right? 1 versus 1.5. So we'll use a different color. And now I don't have the luxury of the line, the dotted line there, but let's see if I can. And it has to be anti-parallel to, oh, that's interesting. I didn't know I called for an arrow. Okay. So that red one is a little bit less than the blue one. And calculate, yeah, so in this case, the it looks like the final vector is going to be close to the positive y-axis, but it's going to be a little bit to the right, as it looks like that E2 is going to wreck it a little bit, going to pull it towards itself. And to get this now, we'd have to calculate the components. So we already know the components for E1. And, ooh, I goofed here too. Look at that. It's late in the day, and I'm tired. So this one is E1, and then this one is E2. And we can approximate the resultant with the parallelogram method. That's what I did. And now, excuse me. Oh, I'm yawning into the camera. Sorry. And yeah, it's close. It's not precise, but it conveys the idea. And there we go. Okay. So, we have to do some trig, so we'll have to... Well, we know this angle, that helps. So, we got to find out what is this, the Q1 angle. And, wow, why do I keep doing this mistake? This is 2. This is 2. And in here is angle 1. And we don't know angle 1. We have to get it. And then we can... Let's see, can we finagle this? No, I have to do it out. So, oh, but we can be a little clever, I think. Right, so we can use sine and cosine. And so the x component here would be cosine. Cosine of theta 1 just happens to be the x component, which is 3 centimeters. 3 times 10 to the... What is it? 3 times... let's get the sig figs going on. 0 times 10 to the minus 2, and the hypotenuse is square root of 34. So I gotta find out what it is. So I had to know. Square root 5.83. And 10 to the minus 2. So that's just the adjacent over the hypotenuse, right? So we have E1x equals E1 cosine of theta of angle 1. And that becomes 1.59 times 10 to the 4th, I think it was, newtons per coulomb. And we have, this is the cosine of that angle 1. It's just these two numbers, right? So what we have to do is divide 3 by 5.83, actually. And, oh yeah, come on, I'm tired. 3.06, enter. 8, and I just have to do the 3 divided by 5.83 because the exponents will cancel. So this. Oh, yeah, not equal. Oh, come on. I just spend so much time looking for the cursor, too. So this is 5.25 times 10 to the negative 1 is the cosine of the angle. And so, let's see, enter 1.59 e to the fourth. Oh boy. A mess going on here. 1.59. And it's not the minus 4, it's just the fourth. Enter. And 5.25. Exponent, change the sign of the exponent. And it's negative 1. And we multiply them to get 8, 3, 5 times 10 to the third. So still a pretty big number. And that's newtons per coulomb. And now we notice that the sine of angle 1 is going to be opposite over hypotenuse. And, oops. Well, where was we? Oh, for the life of me, I don't even know why I'm looking there. Okay. And the opposite in this case is the y value. So it's 5 times 10 to the minus 2. Now, why am I doing that? Oh yeah, 5 times 10 to the minus 2 divided by 5.83. It's the same magnitude. It's going to be, I think it's close to 90. And yeah, that's it. So this is E1x and E2x to y, E1y equals E times sine of alpha, and 1.59 times 10 to the fourth newtons per coulomb. And then we can just jump the gun and divide 5 by 5.83. And we get 8.58 times 10 to the minus 1. And, well, that's dimensionless, right? Okay. And then 1.59 e to the fourth. Huh. Alright. And, I'm trying to do something went wrong. So 1.59 E4, enter. I think I'm falling asleep. E minus 1 times. And I get, still pretty big, 1.36 times 10 to the 4th newtons per coulomb. Well, that makes kind of sense. We guessed that the X component here would be pretty small, and it is. Okay, then now in this case, what can we do? Oh, we know the angle, and we see their opposite internal angles here. So that's going to be equal to angle 2 at the same time. And we can get the components for that and then add them together. Calculate E total at Q. Draw this vector including scale. Right. So we can't just add them together in quadrature like it's Pythagorean theorem, because we can't assume that those two vectors are at right angles to each other. They're most likely not. Well, they do kind of seem it though. But we get the components of E2, and then we add the components up. In the case of B2, we should notice that it's going to be negative. All right. So, half an hour on one problem. Yeah, see, this, I think, ended up being too long of a problem. Okay, let's stop.